the first thing that I want to do is look at these, okay, because it wasn't completely clear that you really knew deep down the difference between all of these. So one thing that I want to point out is that every single one of these is used to prove H implies C. So when you're done with a direct proof, you've proved H implies C. When you're done with a proof by contrapositive, you've proved H implies C. When you're done with a proof by contradiction, you've proved H implies C. All three of these are proving the same thing, okay? And so when I said, explain the general approach for the proof, some of you just said, here, H implies C. So that's not, like, I was really gracious and even gave you partial credit for that, even though you said to me, if you want to prove H implies C, just say H implies C. You're done. Like, wouldn't it be nice if we could just do that? If I wanted you, and you just said it, and then you were done. Like, it would, no, like, it's not very convincing, because then you can just say anything. Okay, so it's important for us to recognize, like, in each one of these, what we're saying is true at the beginning. And then based on what we think is true, or say is true, what we have to show is true from that. Okay, so each of these has a starting point. Okay, so for a direct proof, our starting point, we would just start by saying that H is true. That's where we start. Okay, so we say, given that I already know H is true, where can I go from there? So that's the starting point for a direct proof. Okay. For a proof by contrapositive, I'm just going to go on the starting point so you can see that they're different. So our start by saying, for this one, because I'm doing a proof by contrapositive, I start by saying that the opposite of the conclusion, so not C, is true. So that's where I start on that one. And then I try to get somewhere from there. If I'm doing a proof by contradiction, I start by saying that the hypothesis is true. Okay, so those are my starting points for each of the places. Okay. And then each of these, then I use some kind of valid logical argumentation, okay, of using definitions, rules, theorems, whatever, basically relying on like modus ponens and like those kinds of things. You don't necessarily say you're using those, but that's what you're using, okay? And then I have to show something. So here I show that C is true using valid arguments, right? Okay. So I start by saying I already know H is true. Given that H is true, where can I get from there? Okay, and then I show that C is true. When I'm doing a proof by contrapositive, I start by saying not C is true. I already know this is true. That's not in question. Okay, I know that not C is true, and then I show that not H is true, using valid arguments. Okay. And so notice this is, if not C, then not H. That's a proof of the contrapositive. That's logically equivalent. Okay. And then I can conclude H implies C from this one. You're getting H implies C straight out of this one. I can get that simply because it's logically equivalent to the other one. With the proof by contradiction, I start by saying that H is true. I already know that H is true. Anything in the hypothesis is true. And then show that not C produces a contradiction. Contradiction is just false, right? So if not C produces a contradiction, if it's false, well, that means not C is false, which means C is true, right? So I can conclude that C is true. And so here I started with H is true and eventually concluded that C was true. That's where I'm getting that H implies C. Okay. This one had a lot of people were doing stuff with an inverse, explaining something here with not H implies not C, or that's an inverse, not a, okay, the inverse is not going to be used in any of these because the inverse is not logically equivalent to a statement. So you're never going to see the inverse show up in any proof technique. Contrapositive, sure, okay, but never the inverse. So notice, not a single one of these ever starts by assuming that the negation of the hypothesis is true. Okay. So both of these start with the hypothesis is true. This is the only one that's different. It starts with the negation of the conclusion being true. And this one will show that the negation of the hypothesis is true. Okay. This one is tricky because you just have no idea what contradiction is going to show up. Are you going to contradict the hypothesis? Are you going to contradict something else? That's why this one is tricky, because you don't, like here, you know exactly what you're going for. I'm trying to get C is true. This one I'm trying to get not H is true. This one, I just have to produce some kind of contradiction, but I don't know what it is at the head when I'm set out to do it. And that's why I think this one is tricky. Okay. So, before we go on, are there any questions? Does this help at all? Yes.
Is this always going to be like this setup?
It's always the setup. Always the setup. Yes. It should go that way every time. Yes.
So, with my part B, where I said proof by contrapositive, I got partial points. But like I did, like my thought process behind it was like, okay, I start by negating the conclusion and then prove the negation of the hypothesis. But I just written it out as just a logical statement. So, is it just partial points because we didn't get the part where we needed to?
Because if all you wrote was just like not H implies not C, okay, it's hard for me to tell whether you know that you need to say that not C is true. Yeah. So it's really important that you state that that is true, because that's part of the proof. Like you start there, that's your starting point, and everything falls after that. Because this is true, then all these other things fall in place. So if you're not stating that this is true at the beginning, you have no place to start your argument from. So if you didn't somehow tell me that you were starting by saying, assuming, asserting that not C is true, I probably did not give you complete and full credit. Because it wasn't clear to me that you knew that that's what you needed to do. Okay. So let's go through these two proofs and see how this plays itself out over here. Okay. So, in the first one, we're using a proof by contrapositive. Now, of course, this one's a little bit tricky because you don't just have this like easy hypothesis here. So you need to know, okay, that this has the same form as like hypothesis 1 and hypothesis 2, then conclusion. Okay. And a lot of you remembered that if you have that and you do the contrapositive, you can just negate the conclusion and move it to the other side, and negate one of the hypotheses and move it over there. Okay. So, negating the conclusion and moving it over is great, and then you have to choose which of these you're going to negate and move to the other side. I mean, you can move both of them if you'd like, but when I look at this, I go, wow, this x divides z is so nice. Okay, I want to keep it there because it's not a negated kind of statement. I like that one. This x doesn't divide y. That one is not so nice. So if I negate that one and put it on the other side and negate this one over here, then everything is written in the affirmative, and it's much easier to deal with, right? So if I rewrite this as, okay, I'll just use these letters and then we'll write it out. So if I can say, all right, I'm going to keep H2 because I like that one. Okay, so I'm going to negate hypothesis 1 and I'm going to negate the conclusion and swap them. That is still equivalent to the contrapositive. But notice why this makes it so nice is when I negate this, x doesn't divide, I get x does divide. So I'll have x does divide y minus z here. Okay, H2 is already this nice x does divide z statement. And then when I negate hypothesis 1, okay, the negation of x doesn't divide is x does divide. And now everything's written in the affirmative, and it's so much easier to work with, right? So if I work with that, okay, that is my contrapositive, and that's what I want to do. Okay. So, just like we said over here, we're going to start by saying that not the conclusion is true. Well, in this particular case, it's going to be not the conclusion and hypothesis 2. Okay. So when we have multiple hypotheses, it could be not the conclusion and all the hypotheses that you kept. Okay. But we would start by saying that in our proof. Okay, so we would say, let x, y, and z be integers such that x divides y minus z and x divides z. So notice, there's where I started by saying that my hypothesis... Oh. There's no light coming out of there. Let me just see if I restart this. No, it's just dying. I'm just going to try to restart it and see if we can... There's no light coming out of the little projector there. It's like... Okay, start it. Now the light is on. Well, we could always go back to trying. Where's the... This one. Okay. All right, hopefully that will work. All right, so as we were saying, notice that we should start by saying that the negation of the conclusion is true, which is right there. And then in this general form where we have multiple hypotheses, we would also have to hang on to those ones also being true. So when I rewrite as a contrapositive, anything in front of my arrow, I start by saying that that is true, right? So I say that those things are true. Okay. And after you've said that something is true, like something is an even number, or something is an odd number, or something divides something else, or something is a rational number, you should plan on using the definition of those things. Okay, so an unreasonable number of you never mentioned the definition of what divides means in your proof. So if you're trying to prove that something about divides, you're going to have to use the definition of divides in the proof. Guaranteed. So you better know the definition of divides, you better know the definition of even and odd, and you better know the definition of rational number, because every single one of those is on the test. Know the definitions. They have to be used in the proofs. If you don't use them, the proofs are easier if you use the definitions. Okay, seriously, they are. They're much easier if you actually use the proofs. Okay. So, Now, it is a good idea for you to actually say here, and this is what we've been doing, like what your goal is to show so that you know when you're done. I know for a proof by contradiction, you don't always know. My goal was just to get a contradiction, but up here I know what my goal is. So if I say it and everybody knows what it is, then everyone knows when I'm done. Yes?
To get this cemented in my mind, for contradiction or contrapositive, if we're trying to negate something, like if we're negating the hypothesis, and it's an and statement, we only have to negate one of them, or we can negate both of them.
So if you decide to, so if you were negating like for this one, if it was a proof by contradiction and you're actually negating the entire conclusion and it happened to be an and or statement, yes, you would have to negate the whole thing, and you would have to use De Morgan's law, and you would have to turn it into not this or not that, right? Okay.
So, real quick, repeat that. I need to write that down.
So, if you're negating an expression that involves an and or an or, then you have to use De Morgan's law and negate it, correctly, logically correctly. Okay. The only reason that we're not doing that on the contrapositive is because we know that I can just negate part of the hypothesis. If the hypothesis is that are all anded together, I know that I can just negate one of those and swap it with the conclusion. But let's say there was an and over here in the conclusion. I would have to take the whole conclusion and move it over. Yeah. But it's usually more likely that you're going to have multiple hypotheses than multiple conclusions. Usually a theorem or a statement you're trying to prove is usually just, if this and this and this and this is true, then this one thing is true. Usually things are written simply like that. It's much more likely that you're going to have multiple hypotheses than multiple conclusions. Okay. And so with a proof by contrapositive, you could negate all of those hypotheses and move them to the other side, but then it doesn't make it easier. That's the reason we didn't do it. Okay. Because this is logically equivalent, and this is the easiest way to think about it. Okay, so I think it's a good idea for us to say, okay, I know that I'm going to have to show that not H is true using valid arguments. So if I just tell everybody what I'm trying to show, that reminds me and everybody that's reading it what I'm trying to show. Okay, so you will say, we will show that, okay, and going back to my statement, well, here's the negation of the hypothesis that I chose to negate. So we will show that X divides Y. And if I do that, that is logically equivalent to the contrapositive, which is logically equivalent to H implies C, and so I will have proved it. Okay. So this is the stuff that I know already is true. This is I don't yet know if it's true. Okay. So what you definitely would not want to do at this point, which I did see some people do, is say something like, well, we know there exists an integer a such that y equals ax. I don't know that. Okay, I'm trying to show that that's true. I would like to get to that point, but I don't know it. This is what I have to convince you of, that there is some integer that I could write, that integer times x equals y. Then I can convince you, but I don't know whether this is true or not. That's just what I'm trying to convince you of. What I do know is that x divides y minus c and x divides z. I do know those are true, and so I can find integers such that an integer times x is y minus z and a different integer times x is z. Okay, these things are true, so I can use the definition on these. This, I don't know if it's true. I'm trying to convince you that it is. Okay, so don't apply the definition to this one because I don't know if it's true yet. That's my goal, is to help you show that it's true, but I don't know that it's true, and I can't use something to prove itself, right? Okay. So, at this point, I have to look at what I know is true and apply definitions to what I know is true. So I know two things are true, this one and that one. All right, so if those things are true, then I know the definition of divides, and I just use that definition of divides. So, by the definition of divides, okay, we know that there exist integers a and b, we'll just call them a and b, such that, all right, well, this one I know is true. That means I can take y minus z and write it as a multiple of x. This one I already know is true, so I can take z and write it as a multiple, an integer multiple of x. And that's by definition. You're gonna have to use the definition. Don't try to write the proof without the definition. Okay. And in the back of your mind, you know, here's your thought bubble. Here's you writing a proof with a sad face. And you have this little thought bubble that's coming up, and you're like, oh no, what do I need to show? Okay, so I need to show y equals x times some integer. Like, that's my goal. If I could just get to the point where I have y equals x times some integer, well, then I know that the definition works for this one too. Now, I can't assume that it does off the bat, but the way that I'm going to show that x divides y is to show that I can write it that way. Okay, so if that's my goal, I need to show that. I'm going to need to get y all by itself, isolated, and have some expression that it's equal to, and see if I can convince myself that it's x times some integer. So, what could I do with these two equations so that I could get y all by itself? When I look at those, I go, oh look, I have this negative z and this z. If I just added these together, I would just have y. Okay, so if I just add these two equations, gives us, when I add these two, I just get y, and when I add the other sides, I get ax plus bx. Okay, and still, my frowny face over here that you can't see is starting to turn into a smile because I go, oh, as I'm so close to getting y equals x times some integer, if only I could just write it like that. Could I write x times some integer? Well, I could write it as x times a plus b at least. And now all I need to do is convince you that that's actually what I put there is an integer, right? I have x, I have y equals x times something. I just need to convince ourselves that this is an integer. Okay. Would it be easy for me to convince you that a plus b is an integer? Yes, because the integers are closed under addition. So clearly a plus b is an integer. So since the integers are closed under addition, a plus b is certainly an integer, right? Because we knew that a and b were already integers, so if I add them together, they have to be an integer as well. Okay. And so now I have exactly what my little thought bubble was hoping for. I have y equals x times some integer. And so, therefore, by definition, we know that x divides y. That's what I said I would show, and I just showed it, and that's why I know that I'm done and I can put my little box there. All right, questions about that one? Does that make sense? Yes?
This might be what he was asking and I just missed it. Why is x divides z, why is that not negated?
Okay, because I kept it as a hypothesis. I didn't put it on the other side. Okay, so there are lots of options that we could choose from. Okay, so if I just want to go straight contrapositive, okay, I would say, all right, well, I would have to do not C implies, and since I have this, it would be not H1 or not H2. That's an option. Okay, but notice what that is. That it would be x divides y minus z implies x divides y, or x does not divide z. Okay, and so trying to prove that this is true or this are true, first of all, is really hard to do an or. Okay, also doing a not divides is hard. Okay, so certainly I could try to prove that. It's just that it's really hard to prove that. Okay, and so we know that if we have multiple hypotheses, we already established that I could, if I just move one of them, negate and swap one of those with the conclusion, it's logically equivalent to the contrapositive. And we went through a whole truth table to do that. Okay. So because we know that, we're just going to use that to our advantage. So we could negate this hypothesis and swap it with this one. But then again, we would have x does not divide y and x does divide y minus z, then x does not divide z. And we have all those not divides still in there. So we just try to do it in a way where we can get rid of all the not divides and just have divides. And that way it's easy to think about. Yeah. So yes, you needed a little bit of, mathematical intuition to know which hypothesis to keep and which one to switch. Okay. But now that you have this mathematical intuition, you all know what to do on Thursday if you see something very similar to this, right? Okay, so if you see multiple hypotheses, keep the easy one, switch the hard one. Okay, because it makes it much easier. Okay. All right, this next one. So we're using a proof by contradiction. Here's our pattern. All right, we're going to start by saying that the hypothesis is true. And notice, once again, we have like multiple things in our hypothesis. So this is our whole hypothesis, this compound statement, and this is our conclusion here. Okay. So when we write our proof, okay. I guess we should have said we're going to use a proof by contrapositive, but we already agreed on that, so I'll put it here though. We use a proof by contradiction. So we know our proof by contradiction, we're going to start by saying that the hypothesis is true. We always start there. The hypothesis is definitely true. Okay, so we say let A intersect B be a subset of C, and X an element of set B. Okay, so we always start by saying our hypothesis is true. Okay, and then let's just say we will show that, okay, if X is actually an element of A minus C, we get a contradiction. So that can just at least remind you of what you're setting out to do. Okay, so we're going to show that if I take the negation of the conclusion, so here's the conclusion, X is not an element of A minus C. So there's the negation. It is an element of A minus C. So if I have that, then I'm going to get some kind of contradiction. Okay. So we already know these two things right here. We know these are true. Okay. So, if X is an element of A minus C, then what would be true? Okay, well we know then that X would have to be in A, and that X would not be in C. Okay. And I know a lot of you just went straight to the X is an element of A intersect C bar. Okay. So this is just another way of saying that if X is an element of A intersect C bar, that means it's in A and it's not in C. Okay. So that's what A minus C is. I took A, and anything where C and A overlapped, I took all that away. So if X is in that part that got taken away, it has to definitely be in A, but it wasn't in C because it didn't get taken away, right? So, okay. And so far, I haven't used anything that I know to be true, just the thing that I'm trying to say, well, what would happen if this were true? So I'll go back and look at, well, what do I know that is true? So I know something about A intersect B, but I don't yet at this point know X's relationship to A intersect B. But I do, if I look at this, A is in B, and if this were true, then X would also be in A. Okay. So since X is in B, I have it's in B, I have it's in A, X has to be in A intersect B, right? Because it's in both of them. There, which I know is true, and this one, I'm seeing what would happen if this were true. Okay. Well, if X is in A intersect B, and A intersect B is a subset of C, then every element of A intersect B is also an element of C. All right, so since X is in this, and that set is a subset of C, X has to be an element of C as well. And there's our contradiction, right there. Okay, so here we've said that it's not in C, and here we've said that it is in C. It can't be both. It's one or the other. It can't be both. Okay, so once we get that contradiction, we follow that back and say, well, that contradiction, that contradiction was what would happen if X was in A minus C. Well, I got that contradiction. I didn't know if it was true. I was just saying what would happen if it were true. And now that I see what would happen if it was true, then I would come to a contradiction. So this can't possibly be true. Okay. So I say thus, X isn't actually in A minus C. That couldn't happen. Now this stuff is still true. The stuff that I put at the beginning. I can never say that that stuff is false. That's true. It's only this one that I'm kind of pursuing. Okay. And so notice I've said if H is true, which I have, then C is true. So that's giving me that H implies C as well. Yes. Okay. And a lot of you explained this in words. Okay. But it's much easier to explain in math than it is in words, actually. Like, it really is. Like, that's, I mean, when you do it formally then it's a lot easier to see than if you're just trying to, like, do this high level. All right. All right, so a couple of things. So when we do proofs, there will be a proof that has a divides on it. So it's really important that you know the definition of divides. Okay, and you definitely, so what I don't want to see is, I saw some people, you know, I'm trying to prove something about divides, and then you say here, come down here and tell me something about, well, if X is an even number, then X equals 2 times. This has nothing to do with even numbers. If they're like, so imagine that I said, I'm going to prove to you that Superman is a better superhero than Batman. Okay, I'm going to prove it to you. So first of all, Pokemon, what's his name? Pikachu has Thunderstrike. And so Thunderstrike is effective against, like, I don't know what type. I don't play Pokemon, but my kids do. Water types. Okay. So would you be looking at me like, what does that have to do with Superman and Batman? Yes, you would be. And that's when I was reading some of your proofs. That's what I was doing as well. What does this have to do with divides? So if this is a statement about divides, I don't want to see anything about even numbers or odd numbers. Okay, I want to see something about divides. Okay? Similarly, if I ask you to prove that, you know, if these two even numbers, you know, something about they're even or odd, I don't want to see anything about divides, or I want to see stuff about even and odd. If I ask you to prove that something is a rational number, I don't want to see anything about even and odd. I want to see something that gives me the definition of rational numbers. So know the definitions and only mention those things when the proofs are about those things. Don't just bring up random things, or I'm going to put Pikachu has Thunderstrike on your paper. Because it doesn't matter. Those things don't matter if I'm not talking about that. Okay. So that's one thing to be aware of. Like, keep your focus. Oh, divides. Like, I should be talking about the definition of divides here, and don't be distracted by other things. Like, I do know the definition of even, though. I'll write that one. No, it doesn't. It doesn't actually make it look better. It makes it look worse. Yes.
I just have 2 questions.
Okay.
Are each of the definitions on the study guide that you put up that we need to know?
I said that you need to know them. Shall we review them at this very moment? Okay. Okay, so here's the definition of even. Okay, if x is even, then there exists an integer a, b, m, q, I don't care what you call it, some integer, okay, such that x is 2 times that integer. So I can write x as a multiple of 2 if it's even. Odd. If x is odd, then there exists an integer such that I can write x, okay, as an even number plus 1. Okay. Because if I go consecutive, when you're counting in integers, you get an even number, then an odd number, then an even number, then an odd number. So if I take an even number and go to the next one after it, it has to be odd. So the definition completely makes sense, right? I go to the number after an even number, and that will be that odd number. So that's odd. We have divides. If x divides y, then there exists, I'm going to go for C, an integer C such that, so y can be written as some integer multiple of x. Okay. So this is just saying x evenly divides y. So if I divided both sides of this equation by x and I ended up with y divided by x, the answer would be an integer. C is an integer. Okay, so it makes sense. Okay, it evenly divides it with no remainder. As divides, then we have a rational number. The definition of rational. Okay, if x is a rational number, then there exists 2 numbers. I'm on D and E now. Okay, they both have to be integers. And one of them, okay, because rational, ratio, so we're thinking about, we're going to write a fraction for it, and you can't have 0 in the denominator of a fraction. So we'll just say E is going to be our denominator. That one can't be 0. Okay, so that I can take my x and I can write it as a ratio of those 2 integers. Of course, the denominator definitely not being 0. So you definitely need to know every single one of those. So if there is a proof about even or odd parity, okay, associate the word parity with these. The parity of a number is, even or odd. Those are 2 choices for the parity of a number. A number can be even, can have even parity or odd parity. But those are the things that you need to know. And those definitions better appear in your proofs, okay? But only if the proof is about that thing, okay? So if I'm asking you about rational numbers, don't give me odd numbers. Just give me rational numbers. Okay, so any other questions about these proof techniques? Because, yes.
Do we need to know when to use a proof technique?
I will tell you what proof technique to use. There's a proof by cases, there's a proof by contradiction, there's a proof by contrapositive, there's induction. All of those. Yes?
Well, we need to know how to prove using sets.
There's nothing involving sets.
You guys said proof by cases, proof by...
Cases, contrapositive, contradiction, and definitely induction. More than one induction. So speaking of induction, let me put this down for a second. So there are a variety of different induction examples that we did. So these are the ones that you should especially study, I would say. The closed form for a summation. So you have a summation of something, and then I tell you, oh, here's a formula that you could use so that you don't have to do all the work of adding up a billion things. Okay, so you might want to write that one down. If we don't, we might not have time to do all of these. Okay, but I would try that one of those out. All right, so you're gonna see that. Okay, explicit formula for a recurrence relation. We did those as well. So where you're given some kind of recurrence relation definition, and again, recurrence relations are a pain because if I want to know the 100th thing in the recurrence relation, it's based on the 99th, and if I want to know the 99th, and so calculating things with a recurrence relation is very painful. So if you could ever find an explicit formula, it would be very useful. And so you might want to be prepared to prove that some kind of closed form is an equivalent, will generate the numbers in your recurrence relation correctly. Okay. And I know we did a divisibility proof. We probably did like even odd. We definitely did a divisibility. I can't remember if we did an even or odd one, but okay. I'm not going to give you any inequalities because I know those take a lot of creative, you got to be a mathematician and have your bag of tricks, and that's a little bit tricky to do in a test, time pressure situation. So these ones are straightforward, and they shouldn't give us too much trouble. Yes?
We need to know those closed formulas for arithmetic and geometric sequence.
It would be a good idea. I will tell you what you need to prove, but I'll just say it would be a good idea because there could be a bonus opportunity on the exam that asks you if you know how to use those. And so, if you don't want to exert brain cells and you don't care about bonus points, then no. But if you like bonus points, then yes. So depends. I have a serious lack of blank pieces of paper. And all the markers bleed through, so it's hard to. Here's a good one, here's a good one. Okay. All right. Since we might run out of time, you want to do closed form for summation, explicit formula, or divisibility proof first? Explicit formula for recurrence relation. Yeah, good call. Because that's the last thing we did, and it's probably the least familiar. Okay, so we've got this sequence. Let me write it down, and then I'll switch. You write it down too, and let me write it on this piece of paper, and then I'll put my camera back up. Okay, so that's what we know. We have this sequence, okay, and it's defined by this recurrence relation. And we want to prove that I could just use this closed form to give me the nth term instead of having to go through all the pain of using the recurrence relation. Okay. So when we have something like this, Okay, this is what we know to be true. This is truth. Okay, this is what we're trying to prove. Okay, so I don't know if that's true or not. That's my goal, but I can't just, so this stuff I can use it as true. I can't use this as it's true, like, just say it's true. Okay, so if we use a proof by induction, okay, where do we start every induction proof? Base case. What is our base case? 0. Right, so I go over here. The smallest index I can ever use for n is 0, because that's where this sequence starts. So our base case is n equals 0. Okay, and I'm trying to show that this a sub n and this formula, n times n plus 1 over 2, actually give me the same thing, right? So first of all, I'm going to look at the left side, a sub n. Okay. Well, if I want to know what a sub n is, I have to go to something that I know is true, and that's the definition. Okay, so when I substitute in 0 for n, I go over here to stuff that I know is true, and I go, oh, look, there it is. It's 0. I know it is 0. Okay, so that would be the left side of the equality, and now I would go, all right, well, does this expression on the right give me the same thing? So I would want to check n times n plus 1 over 2 and see if it gives me the same thing. Well, when n is 0, I'd substitute that in there. That would be 0 times 0 plus 1 over 2. 0 times anything is 0, so that's definitely 0. And yay, they match. So a sub n equals n times n plus 1 over 2. Okay, for n equals 0, so the base case is, okay, so hooray, it works for the base case. Okay, and the next thing is our inductive step. And our inductive step, we make an assumption. And what are we going to assume? Good. So that the thing that we're trying to prove is true, we're just going to assume that it is true when we put k in there. So assume that the kth term of the sequence is equal to k times k plus 1 over 2 for some integer k that's greater than or equal to 0. Okay, since that's our starting point. So now, what we can work from are things that we know to be true here and things that we assume to be true here. Okay, so we have this that we know is true, and we have this that we're assuming to be true. And those are the things that we have to work with. Okay, and we want to show that if this is true, then the one after it is true. Okay, that gives me the implication. The case for k implies the case for k plus 1, and that implication together with the base case that sets off the chain reaction allows us to get it for every single value of n greater than or equal to 0. Okay, so all we're going to get, from this inductive step is an implication. If it's true for k, then it will be true for k plus 1. Okay. Not that it's true for every n. That only works once I pair it up with the base case. But we're going to go to the next one. So I'm going to show that if this is actually true, then when we go to the next one, a sub k plus 1, and substitute k plus 1 in everywhere, that will be true. So once again, just like I did before over here, I've got to go to both sides of the thing that I'm trying to prove. I've got to go to the left side, okay? And I'm going to see if I can transform the left side into the right side to show that they're equal. So I'm going to look at the left side, a sub k plus 1. Okay. Well, what do I know to be true? I know this definition is true. And I know, I'm assuming that this is true. That's all I know. Okay. So this isn't telling me how to find this, but this is. If I want to find, a sub k plus 1, here's the rule right here. To find any term, n, I just go to the previous one and add whatever the index is to it. All right. So I just use this rule by the definition. Okay, if I'm finding the k plus worst term, well, that's really k plus 1. So I go to the one that's before k plus 1. That would be k. So I go to a sub k. And then I would add on whatever index I'm trying to find, which is k plus 1 in this case. Okay, so I'm just using this definition by the recursive definition. Or the recurrence relation. So again, I go back to the things that I know are true and the things that I'm assuming are true. And now, here, this thing that I assumed to be true can come in handy because I can now make this substitution. Since I assumed that a sub k was this, I can just substitute that closed form for a sub k right there. All right, so I can take and do k times k plus 1 over 2 and make that substitution. And the only reason I can do that is by the inductive hypothesis. Okay. And hopefully at this point it's just a matter of algebra. Okay. So I basically want to get this to look like that. Okay, well, it's all written as a single fraction with a common denominator of 2, so that's a good place to start. Okay, I'm just going to expand this one out, k squared plus k over 2. And if I want to write this with a denominator of 2, I'd have to write that as 2k plus 2 over 2. So yay, I've got a common denominator, and so that's going to be k squared plus 3k plus 2. And then if I just factor that numerator, okay, it factors and looks exactly like that. So now, okay, using only things that I knew to be true and this inductive hypothesis, I showed that these two things are equal. It's all based on either what I know to be true or this one inductive hypothesis, this one assumption that I made. Yes. Okay. And so, if we had forgotten that, all I would have is that if it's true for k, then it's true for k plus 1, but I have no idea if it's true for k, right? Just that alone does nothing for me. But now I put it together with the base case, I go, I know it's true for 0. Well, if it's true for any k greater than or equal to 0, then it's true for the next one. I know it's true for 0, so that means it's true for 1. Well, now I know it's true for 1. Well, I know if it's true for 1, it's true for 2. Now I know it's true for 2. But I know if it's true for 2, then it's true for 3. Now I know it's true for 3. And so you get this chain reaction, and now it's true for every single n after 0. Okay. But both of the parts are important to put together. You can't just have one or the other. You have to have both of them. Okay, so now you put those two together. This starts the chain reaction. This keeps it going on forever. And that's the principle of mathematical induction. So therefore, by the principle of mathematical induction, we know that that formula is going to work for every single value of n that's greater than or equal to 0. Now, will it work for -1? No. If it was anything less than our base case, I have no claim about that. Only for my base case and greater. All right, we probably have time for one more. You want to do the summation or the divisibility? Summation? Okay. Can you guys tell me what the summation one was? No, did anyone write it down? No, you didn't.
Prove that the sum of the first n even positive integer is n plus 1.
All right. All right. So the sum of the first n positive even integers is n times n plus 1. So let's think about like what that's saying. That's saying I would take, like, what's the first positive even integer would be like 2, and then the next one would be 4, and then the next one would be 6, and I'd keep going on and on and on. Okay, and if I'm doing the first n of them, okay, what would the nth positive integer be? 2n. Okay. So basically, we're asking to prove that this sum is equal to n times n plus 1. Okay. So let's write that as a summation. So the summation I equals blank to blank of blank. Okay. So how would I write this as a summation? So how many things are we adding together? We're adding n things. Okay, so this index, there better be n different indices. So probably it makes sense to start at 1 and go up to n. That would give me n different things. Okay, if you wanted to start at 0 and go up to n minus 1, you could, but that's not very natural. Okay, so when I put I as 1, I want to get this thing. When I put I as 2, I want to get this thing. When I put I in as 3, I want to get that thing. When I put I in as n, I want to get that thing. So what expression should I put here in my summation? 2i. I heard it. Good. Okay. So this is the sum of the first n positive even integers. And I want to show that that sum is always going to be n times n plus 1. Okay, so that's my goal. So we use induction on n. Okay, we know we're going to start with the base case. And what is the base case? Yeah, what does it say it again really loud? 1, right. So the smallest value I could ever put in for n is 1, because if I start at 1, I could stop there as soon as I start, but that's the smallest I could be. So base case is n equals 1. Okay. And so I want to show that the left side, okay, this summation is going to be the same thing as the right side. So first I'm going to look at the left side. The sum I equals 1 to n of 2i. Now when n is equal to 1, I'm just going to replace that n with a 1. That would be I equals 1 to 1 of 2i. Okay. Well, I know how to find a summation. I just start at the lower index, okay, at 1. I substitute that in there, and then I stop when I reach the upper index. I've already reached it. Okay, so there I am. It's 2. So that's the left-hand side, and now I go look at the right-hand side. So the right-hand side, when n equals 1, I put a 1 in for n, and I have 1 times 2 equals 2. Hooray, they match. Okay. So the summation works for n equals 1 for the base case. Okay, then I have my inductive step. So remember the inductive step. I'm just going to say, well, let's assume that this summation works for some arbitrary value of k. So I'm going to assume that the summation from I equals 1 to k of 2 to the I equals k times k plus 1 for some positive integer k. I can just say that since we start at 1 and that's the first value in there. Okay. And then, of course, we want to show that if I go up to k plus 1, then I can substitute k plus 1 in this formula, and it all still works wonderfully. Okay. But this is the only thing I can use. All right, so I'm trying to prove something about the sum up to k plus 1. So if I can rewrite it in some way in terms of this inductive hypothesis, then I can use this inductive hypothesis. I mean, my whole goal is to be able to use this inductive hypothesis. Okay, so with the summations, we always rewrite it in terms of the previous one, the inductive hypothesis. So if I take this, I equals 1 to k of 2I, okay. Certainly those two things aren't equal. There's more stuff here than there is over here. So I have to add on whatever I'm missing. So what am I missing, okay, when I make this stop at k and not go up to k plus 1? Like, what am I missing? What do I still have to put there? Two times k plus 1, right? So we have to, when I gets up to this right here, that's going to get substituted in for I, and that I never got there, right? I stopped before I got there. So I have to add on that last one that would have gotten added on if I ever had become k plus 1. Okay, so I'm missing the 2 times k plus 1, the very last thing that I would have gotten to had I went all the way to the upper bound of my index there. All right. And so the whole reason that we wrote it this way is because now I can use this inductive hypothesis. So this and this are exactly the same, so I can replace this summation with k times k plus 1 by the inductive hypothesis. And now it's all a matter of algebra. So I've got a common factor of k plus 1 that I can factor out. So just factor out that k plus 1. That first one I have to multiply by k, and that second one I have to multiply by 2. And that's exactly what I was hoping for, right? Okay, now I've showed that this left side indeed is equal to the right side as long as the inductive hypothesis is true. So if the inductive hypothesis is true, then the k plus 1 case is true. All right, so thus by the principle of mathematical induction, that formula is going to work for all n as long as they are integers starting at 1. Okay. Can't start it at 0 because that's less than my base case. So it has to be positive integers. It has to only be the ones base case on. All right. I don't think we have time to do the last one, but you should try it. Do you want me to put it back up there? You guys need to copy that last one down, anybody? The divides one. Try this one out, the divisibility one. Let me know if you get stuck. Try that one.